All right. So I ended last time. I was starting to talk about what the stress, where the stress tensor comes from. Oh, before I get back into that, I just was told this morning that today is the last day to drop for full refund. So if that matters to anyone, you should do it today. Okay. So at the end of last time. So. Last time I started a description of where the stress tensor comes from. And the idea is we're trying to represent the loading at a point, at a single point. So we start out with the idea of a finite cube of material, and then we take the limit as the size goes down to 0 to shrink down to the point that we want. And as you shrink down, the couples, the moments produced by the couples shrink faster than the forces, and so the couples end up not being important. And so, excuse me, if you take the limit as the cube approaches 0 size, the loads can be represented by a vector of force per area on each face. So this cube is infinitesimal. As you take that limit down to 0 size, the forces also go to 0, but the force per area doesn't. So the force per area is a finite thing. And you end up with a force. So if this is the coordinate system, you end up with a force vector on the x face, a force vector on the y face, a force vector on the z face, and then the way I've drawn this cube, you can't see the negative faces, but there are force vectors on each of those two. Oh, and these should be divided by areas. Okay, so each one of these vectors, so there's a total of 18 force per area vectors. Force per area values. Divided up into 6 different vectors. Each one of these vectors is called a traction. So it's called a traction, and it represents the loading on one face of the cube. we're going to be able to simplify this down some, and it's going to come from two sources. We're going to be able to go from 18 values down to 9 values using Newton's second law, and then from 9 down to 6 using rotational Newton's second law. So Newton's laws for equilibrium allow us to simplify this. Allows us to reduce the number of loads. First, Newton's second law, in order for that to be satisfied, every negative face, the tractions on every negative face have to be equal and opposite to the traction on the positive face. So equal and opposite to the positive face tractions. So now we can represent all the loads uniquely with only 9 values. We only need the tractions on the positive faces. Let's say the positive axis faces. And when I say the positive axis faces, think of the origin as being right in the center of the cube. And so each axis is pointing out from the center, out of the material. And so this on the right side is the positive x face. This on the top is the positive y face. The one towards us is the positive z face. So we went from 18 down to 9 values. And then the moment equation in equilibrium, that says add up all the external moments, and those have to add up to 0. Rn2L, that's rotational Newton's second law. I don't know why I got in the habit of writing it that way, but get used to it. That says that I'm not going to explain why. You might, if you feel like thinking about it, you might be able to make sense out of why, but says that flipping the subscripts, anytime you flip the subscripts of a, well, there's no subscripts yet. Let's see. Let me draw it. It says that this component of the traction has to equal this traction. This has to equal this. And this has to equal this. You could calculate the moments produced by all these loads with an about point at the center of the cube, and you could see that there's no way to meet moment equilibrium without those being equal. And so what that says is that 3 more of these values are redundant. So we've gone from 9 down to 6 values. And we'll represent this in a symmetric 3 by 3 matrix. So the matrix looks like this. Sigma is the name of the stress tensor. The stress tensor is this matrix. So we have sigma xx, sigma xy, sigma xz. In the middle we have sigma yy, and then symmetry says that, you know, you would think following this pattern this would be sigma yx, but it doesn't have to be because of this, because of what we just figured out from the rotational equation, the moment equation. So we'll write this as sigma xy again. Yy and then yz. And then we'll write this one as xz, yz, and zz. This has 6 independent values, and this stress tensor is equivalent to this cube. On the positive x face, we have a component in the x direction, a component in the y direction, xy, and a component in the z direction, sigma xz. On the y face, we have a component in the x direction. What's the name of that one going to be? Yep, yx. And then the one in the y direction? YY, and then in the z direction? YZ. So the first subscript refers to the face that it's on, and the second subscript refers to the component direction. And then the third one, on the third face, on the z face, there's the component in the x direction. What's the name of that element? Yep. Yeah. I guess I did. Sorry, I don't mean to make this a mess, but let's use the symmetry here. So let's change this one on the y face, the one in the x direction. Let's call that xy. So now in the z face, this one is xz. In the y direction, this one is yz. And then in the z direction, zz. Bless you. And so every stress tensor, there's this, every stress tensor corresponds to a stress element, one of these infinitesimal cubes, and this is what the meaning of each one of those elements is. Okay. The diagonal elements of the stress tensor are the normal stresses, a positive value means that the member is in tension, and a negative value means it's in compression. Okay, so these are the diagonals. And where they show up on this stress element are the components that are perpendicular to the faces. That's why they're called the normal stresses, XX, YY, and ZZ. And the off-diagonal elements of the stress tensor are called the shear stresses. The positive and negative don't really have a qualitative meaning the way they do for normal stresses. It's just directions. But that's all the ones that aren't circled in red here are shear stresses. And that name comes from the fact that if you so why are they called that? If you imagine taking a set of shears so there's the material you're looking at. And you use these shears to cut that material along this line. Can you picture what I'm trying to draw there? You'll have material in the middle on that dotted line. What you're doing to that material is pushing the right side down and the left side up, like this. This is an infinitesimally thin strip representing that dotted line. And the stresses that you develop in warping the shape of that material that way are shear stresses. So you can think of it that way. The name shear stresses comes from the fact that that's what you do to a material when you shear it, when you use shears, cut it that way. Okay. Okay, so let's do a couple examples of, so you can go, there's always this correspondence between a stress tensor and this stress element, this infinitesimal stress element, and if you're given one, you can always go to the other one. So let's say that you have, this is the stress element. So let's say that there's, on the Y face, there's a traction component of 5 megapascals to the left, and to the back there's a traction component of 2 megapascals. A megapascal is 1 times 10 to the 6 pascals. And then let's say that there is also a normal traction on the X face of 10 megapascals. Let's do two things. Fill in the remaining traction components. To satisfy Newton's laws. for equilibrium. And then second, give the corresponding stress tensor. Okay, well, the remaining ones, to satisfy Newton's laws, this one that says 5 megapascals to the left has to be accompanied by a downward 5 megapascals on the x face. The 2 megapascals going to the back on the y face has to be accompanied by a 2 megapascal stress going down on the z face. So that's all we need to do for A. And then for B, the stress tensor, what's the XX element of stress? Yep. -10. What's the XY component of stress? Yeah, -5 because it's going in the negative y direction. All of these are just the regular coordinate system sign convention. So -5. What about XZ? 0. Then symmetry says -5 here. What about YY? 0. What about YZ? -2. And then symmetry says this is 0, this is -2. And then what about ZZ? 0. And all of these are megapascals. Here, let's do another one. So let's do one where we go the other direction. So let's say the stress tensor is 1, 2, 3, 4, 5, 6, 7, 8, e to the pi. You didn't expect me to say that. Megapascals. Let's change that to a 9. Okay, so, oh wait, we can't do that. Because of symmetry, that 4 needs to be a 2. The 7 needs to be a 3. And the 8 needs to be a 6. Okay, so draw the stress element for this stress tensor. Why don't you take 2 minutes, see if you can think through this, and then I'll go through it. Okay, so there's the stress element. X is to the right, Y is up, Z is out of the page. Okay, so the XX stress, so on the X face, the component in the X direction is +1. On the X face, the component in the positive Y direction is +2. And on the X face, the component in the positive Z direction is +3. Now you can put in all the things that are required for symmetry. That has to be 2. That has to be 3. And now we can go to the ones that we haven't filled in yet for the y face. The component on the y face in the positive y direction is 5. The component on the y face in the positive z direction is 6. And that gives us one more requirement for symmetry. And now the z face, we already have the one in the x direction. We have the one in the y direction. We just need the one normal to the face in the z direction. And that's 9. Any questions about that? Okay. So the next thing we have to talk about is a really important relationship between the stress tensor and the traction on any arbitrary face. So the stress tensor shows you the tractions on each one of these faces of the cube, but you can measure the traction on any arbitrary plane, and it's really easy to do once you have the stress tensor. So this is a key relationship between the stress tensor and the traction on an arbitrary face, or let's say on a given face. Let n hat, so this is a normal vector, let this is a unit vector, let n be a unit vector perpendicular to a given face pointing out of the material. This is what people call the outward facing normal. Then the stress tensor multiplied by the outward-facing normal vector gives you the traction vector on that face. This is the traction vector on the given face. And remember, these traction values have units of force per area. So this is like a distributed load. Given as a force per area. Okay, so first let me show how this works with a stress element. That's that's the simple, easiest one to wrap your head around. And it sort of intuitively gives you a sense of why this works. So let's say that we have this stress element. On the x face, the x component of traction is 7 megapascals. There's no y, and the z component of traction is 2 megapascals. So that requires that on the z face you have one like this that's 2. And then on the y face, let's say there's one in the negative z direction of 1 megapascal. That requires, for symmetry, one pointing on the z face pointing in the negative y direction, so that's 1. And then let's also say that there's a normal traction component on the z face of 10. So what's the traction vector on, let's do it for the positive x face, the positive z face, and then let's do it for the negative x face and negative y face. Okay, those are just, I just picked those out. I just didn't want to do all 6, but well, we know what these should be because this stress tensor is defined in terms of these tractions. We know that on the positive x face, we should get a traction that's equal to positive 7, 0, positive 2. On the positive y face, we should get 0, 0, negative 1. On the positive z face, we should get 2, negative 1, 10. And then all of the negative faces should be the opposite of that. So like the negative x face should be negative 7, 0, negative 2. Okay? That's what we need to get. And we're going to do it with this multiplication rule, this stress tensor rule. So the first thing we have to do is go from this to the stress tensor. What's the XX stress element? Positive 7. What's the XY element? 0. What's the XZ element? Positive 2. And then we have 0 here. What's the YY element? 0. YZ element? And that's in the negative z direction, so that's minus 1. Yep. And now symmetry says 2, negative 1. And then what's the ZZ element? Positive 10. Yep. And that's megapascals. Okay, so now for part A, what's the outward facing normal for the positive x face? So go into the material and point out of the material. What's a unit vector pointing perpendicular to the x face from inside the box out of the box? 1, 0, 0. Yep. So n is equal to 1, 0, 0. And so the traction vector is equal to 7, 0, 2, 0, 0, negative 1, 2, negative 1, 10, the stress tensor, times this outward facing normal, 1, 0, 0, and we get a traction vector that's equal to 7, 0, 2. Does that correspond to the traction that we drew in the stress tensor on the positive x face? Yeah. That'd be embarrassing if it didn't. Okay, so now the positive z face. Well, what's the outward facing unit vector, the outward facing normal for the positive z face? 0, 0, 1. So the traction vector is the stress tensor times the outward facing normal, and this gives 2, negative 1, 10. Does that make sense with the stress tensor as it's drawn? So on the z face, the x component is 2, the y component is negative 1, and the z component is positive 10. So that works. So now let's do the negative x face. What's the outward facing normal for the negative x face? Yep, negative 1, 0, 0. So the traction vector is the stress tensor 7, 0, 2, 0, 0, negative 1, 2, negative 1, 10 times this outward facing normal of negative 1, 0, 0. And what do you get when you multiply these? Negative 1 times 7, 0, negative 1 times 2. For this to be an equilibrium, the traction on the negative x face has to be equal and opposite to the traction on the positive x face. So this has to be equal and opposite to what we got in A, and it is. Let's do one more because everybody likes doing the same thing over and over again. So D, what did I say, the negative y face we're doing? Negative y face. So what's the outward facing normal for the negative y face? Yep, 0, negative 1, 0. So the traction vector on the negative y face is the stress tensor times the outward facing normal. And what do you get for this? You get 0, 0, and then negative 1 times negative 1 is positive 1. That has to be equal and opposite to the traction on the positive y face. The positive y face only has a component in the negative z direction of 1. So it's 0, 0, minus 1. So on the negative face, it has to be 0, 0, positive 1. So all those make sense. Any questions about this? All right. This is just sort of shows how it works, but this hasn't showed any of the usefulness of this yet. What's the point of this? What good is this? Well, one, it's important for setting up equations for stress tensors. It provides boundary conditions for when solving for stress tensors. And I'll show how that works. This, by the way, isn't something we're gonna use in this class outside of just doing a couple problems to follow, like the examples I'm going to do here. But when you get into more advanced mechanics, this becomes important. And then second, this we are going to use. It's this process that allows us to calculate principal stresses, which is going to be a really important thing in this class. So this provides the path to calculating principal stresses. How do you know when to spell principal P-A-L and when you spell it P-L-E? It's important for sounding smart, looking smart when you write stuff. So one means like main, you know, like the main thing, the principal thing, the first thing. And one is like stick to your principles, like your main, your foundational ideas. And so the thing that's like the first, you think of like the guy who's in charge of your school, the principal, he's your pal. Okay? So now you know. If you're talking about the first or the best or the, then it's P-A-L. You use both of them in physics, you know, so it gets confusing. Like I don't know, what's...
Principles of Newton's law.
Yeah, right. Okay, so let's see how this works on a face that is not that's not one of the just axis faces, where we're going to have something other than just a single 1 and 2 other zeros in our outward facing normal. So let's say we're looking at a body like this, where this is all solid, and we'll still use this same coordinate system with z coming out of the page. And let's say that this angle is 45 degrees. And if the stress tensor is 2, 0, 1, 0, negative 5, 0, 1, 0, 8, and this is megapascals, what's the distributed load on that diagonal face? Well, we already have the stress tensor. All we need to do is figure out an outward-facing normal to that. So can anyone think of what the outward-facing normal would be for that? Here's how I always think of these. Yeah, right. So if you ever have trouble figuring out an angle of a vector, just, I talk about this a lot in statics, just keep zipping around. Positive is counterclockwise, negative is clockwise, from the positive x-axis to whatever you know. Just keep going to stuff you know from where you are. Okay, so here's the positive x-axis. How do we get, we're trying to get to a vector facing that way, right? Well, I know if I go 180, I'm facing this way, right? So now I'm at positive 180. Now if I backtrack 45, I'm here. So now I'm at positive 135. Now if I backtrack another 90, I'm where I want to be. So 135 minus 90 is 45. Okay. So this is the outward facing normal. And it's equal to cosine of 45, sine of 45. Which is 0.707. I can't do these power series that fast. 0.7071, I think. I'm just kidding. I didn't do any power series. I just use that angle all the time. Okay, so, and then the traction vector then is the stress tensor 2, 0, 1, 0, negative 5, 0, 1, 0, 8, times that outward facing normal. Oh, and I did it in 2 dimensions, but we're doing everything in 3 dimensions, so let's just add a 0 to the end. So 0.7071, 0.7071, 0. And you get a value of 1.414, negative 3.535, zero 0.7071, and the units are megapascals. And so if this is the stress tensor at points on the surface, this has to be the distributed load that's applied externally to this object on that face. Any questions about that? So that demonstrated, like, if you knew the stress tensor, how you could figure out what the external load is that's applied to this object. Usually that's not the direction that you need to go. Usually you're trying to calculate the stress tensor and you can measure the external loads. Those are the ones that are more easily applicable. So let's take a break, and then after we come back, I'll show how to go. It's the same idea, but we're going to go from a known traction on a surface to figuring out what restrictions we can put on the stress tensor at that point. Okay? So now we're going to do an example going in the other direction. So say that we have an object like this, a bar with a square cross-section. So that's 0.1 meters, and this is 0.1 meters. And there's a load distributed over this face I did too many arrows. Okay, so there's a load uniformly distributed over the face that has a total of 25,000 newtons. What restrictions can we put on the stress tensor? That's the question. So what do we know about the stress tensor? At this face. You know, the stress tensor represents a single point in the material, so we don't know that this is going to be true for other points in the body, but we know we are going to figure out some stuff about the stress tensor right at the face where we know this distributed load. So first we have to go from this total force into a distributed load. So we know that the traction on that face is, and if we're using this coordinate system again, that force is acting in the negative x direction, so we know it's going to be negative 25,000 divided by the area, which is 0.1 times 0.1. And then 0y and 0z. And that is in pascals. So that's 2.5 times 10 to the 6th pascals, and then 0, 0. Anybody have any questions about how I figured that out? Oh, that's negative. How I got that? Okay, and now we know that this traction has to be equal to, so negative 2.5 times 10 to the 6th pascal, 0, 0, has to be equal to the stress tensor, times the outward facing normal. What's the outward facing normal to this face? So draw a vector pointing out of that face. 1, 0, 0. And so you get that negative 2.5 times 10 to the 6, 0, 0, is equal to, if you do this matrix multiplication, sigma xx and then 0, 0. No. Stupid. Sigma xx, sigma xy, sigma xz. Okay, so you know that sigma xx has the value of negative 2.5 times 10 to the 6. Sigma xy and sigma xz are both equal to 0. So now you can simplify the stress tensor a little bit. Negative 2.5 times 10 to the 6, 0, 0, you can figure out a little bit of stuff from symmetry. And then there's some stuff you still don't know. You don't know the YY. You don't know the YZ. And you don't know the ZZ. But you've limited the number of variables that you have to calculate at that point. So you've eliminated 3 of the 6 unknowns. Bless you. And, you know, you can do the same thing if you have a face that's at an angle. Like in this case, if you're given some information that you know about the traction, you use that angled outward-facing normal, and you can figure out it'll end up being a little more complicated relationship between those variables, but you can still find some constraints on allowable values for those variables. Anybody have any questions about this? Okay, so that tractions thing, that's gonna keep coming up, mostly when we start talking about principal stresses. And principal stresses are really useful because it lets you calculate in any material the greatest, or at any point, it lets you calculate the coordinate system that gives you the largest tension, the largest compression, and it lets you calculate the largest shear stress, and those are all really important values for figuring out when a material is going to break. So principal stresses that use this are going to be a big thing. Okay, so now let's talk about strain. We've been talking about stress. So yeah, this is going to be strainful. Strain and the constitutive relationship. The constitutive relationship is the relationship between the stress and strain. So when I say the constitutive relationship, I'm talking about how to use Hooke's law for solids. So remember that stress is a measure of loading. It measures the loading at a point. Strain measures the local deformation at a point. When we talk about strains, remember that everything that we're doing is valid for very small strain values. We're assuming small deformations where the strain values are smaller than about 1 times 10 to the minus 4th. So anytime we see numbers bigger than that, and there are going to be some examples that I do where they're bigger than that, it's just not really a physical, it's not a realistic environment. So when we use bigger strains than that, it's not really realistic. So in a general deformation, a cubic element deforms into a parallelepiped. That's a four-sided, four-edged. It's a shape that's made of, I guess, 6 parallelograms. So it goes from this to this. And that requires 2 kinds of deformations. Two deformation types. Length changes and angle changes. The length changes are going to be represented by the normal strains. And the angle changes are going to be represented by the shear strains. It's the same naming as for stress tensors, because there's a relationship between normal stresses and normal strains, and a relationship between shear stresses and shear strains. So the first thing we're going to talk about are the normal strains. Let's say that we start with an undeformed object. I'll make this the x direction, y direction. The z-axis is coming out towards us. And let's say that before the deformation, this is a cube. This length is capital L sub 0, and this length is capital L sub 0. And after this undergoes a deformation, some sides are bigger and some sides are smaller. The lengths are bigger or smaller. I'll call this length along the x direction lowercase l sub x, and I'll call this one lowercase l sub y. And if z is also deformed, then that's, after the deformation, the length parallel to the z-axis. Then the strain epsilon xx is equal to lowercase l sub x minus capital L sub 0 divided by L sub 0. You can also think of this as this Lx minus L sub 0 is the change in length of that side. So you could also think of this as like delta change in length, delta x over L sub 0. And then the other ones are defined the same way. So epsilon yy is Ly minus L sub 0 over L sub 0, or delta y over L sub 0. And epsilon zz is lowercase l sub z minus L sub 0 over L sub 0, or delta z over L sub 0. So that's the definition of the normal strains. What are the units of these? Unitless, yep. The numerator has units of SI units of meters, any kind of units of length. The denominator has units of length, and so those are always going to cancel out. And so you always just get a pure number for the strain. So let's do an example. Let's say that we start out with a rectangular shape where the original x length is 0.01 meters and the original y length is a little less than that. Let's say this is 0.008 meters. And let's use a different coordinate system. So let's say the z-axis is pointing to the left and the y-axis is pointing up. Which way is the x-axis pointing then? Towards us, yep. And after the deformation, I drew this really exaggerated, but after the deformation, the height is 0.011 meters, and the width is 0.005 meters. And let's say there's no change in the x direction. What are the normal strains? Well, first, the strain in the x direction, the normal strain in the x direction. Whatever the final length is in the x direction is the same as the initial, so we have no change in the length divided by whatever L sub 0 is. So if you don't have a change in the length along that axis, you get zero strain, no deformation. Epsilon YY is 0.011 minus 0.008 divided by 0.008. So you get 0.003 over 0.008, which is 0.375. Is that a realistic strain for us? No, it's way too big. For any realistic problems that we do using these methods, this number has to be, something times 10 to the minus 4 or smaller. And then epsilon ZZ. The final length is 0.005. the starting length is 0.01 divided by the starting length. And so you get negative 0.005 divided by 0.01, or negative 0.5. And again, that's way too big, but this is how you calculate it. Okay, so what was the sign convention for normal stresses? What does back to stresses, what does a positive normal stress tell you? In tension. Negative normal stress tells you it's in compression. And the sign convention here goes along with that. If you put something in tension, it increases the length. And so a positive normal strain goes along with a positive normal stress, and vice versa. So notice the sign convention. A positive normal strain means elongation, and a negative normal strain means contraction. Any questions about that? Okay, so these shear strains, I drew a picture earlier of why you call shear stresses, where the word shear comes from. Okay, so when you apply a shear stress to a material point, you push one side up and the other side down, and the effect of that pattern of loading is to deform the material so that the angles change, like I drew it here. Okay, and so shear stresses naturally correspond to shear strains. And so let's talk about how to calculate a shear strain. So shear strains are changes in the angles between faces. And so if your undeformed object is rectangular, so all of these angles between the faces are 90 degrees, and I'll use this coordinate system, x, y, and z towards us. After deformation, the angle between the two positive faces, in this case, this is the positive y face, and this is the positive x face. Okay? They make a new angle of, since we're talking about the x and y faces, this is theta x y. Then the shear strain, gamma xy, is equal to pi over 2 minus theta xy. Gamma xz is pi over 2 minus theta xz, and gamma yz is pi over 2 minus theta yz. This angle needs to be in radians. And so even though you're calculating these strains with an angle, radians are kind of not really a unit, and so you still end up with these being unitless. The sign convention. So notice that if a shear strain is positive, the angle between positive faces gets more acute. And if the shear strain is negative, the angle between positive faces gets more obtuse. Okay, so let's say that we start with this undeformed shape. These are all right angles. And let's use a funny coordinate system where up is the x-axis and to the left is the z-axis. Let's see. And after the deformation, we're given that this angle is 1.43 radians. What's the XZ shear strain? Well, remember that the angle that we care about is the angle between the positive faces. The positive x face is this one. The positive z face is this one. So that angle that was given is not the one that we need to compute this shear strain. We need the angle between this red and this green. So this is the angle that we want. That's theta xz. So let's see. First we have to figure out what that is. If you add up this angle and this angle, they have to add up to 180, or they have to add up to pi. So theta xz plus 1.43 is equal to pi. So theta xz is equal to 1.71 radians. And so now the shear strain, xz, is equal to pi over 2 minus 1.71 so you get a value of negative 0.1392. right now, again, that value is way bigger than we would expect in a physical problem, but that's the way you calculate it. Any questions about that?
Could you scroll back up to your introduction of the shear strains?
Yeah.
Oh.
There?
Go back down a little bit, yes, sir. The next, this definition, yeah.
So yeah, if the positive faces get more acute, it's a positive shear strain. If the positive faces get more obtuse, it's a negative shear strain. Yep.
Instead of doing the beta xz plus 1.43 equals pi, can we just do pi over 2 minus 1.43 and then see what kind of angle it is? If it's obtuse, then we just put negative, and if it's acute, we just leave it positive.
Yes, I guess that's right. Any other questions? Okay, let's do one where we calculate all the strains. So let's say we start with a shape. This time it's a cube. Everything's 1 centimeter long. And after deformation, we have a distance here of 0.015 meters, a distance here of 0.007 meters, and an angle here of 1.3 radians. Everything else that I didn't. So any changes that aren't shown, we'll just assume are 0. And we want to calculate all the strains. Okay, so how many strains are there? How many normal strains are there? Yeah, it's a change in length along all 3 axes, so there's 3 normal strains. And then there's changes in angle between all 3 normal faces, so that's 3 shear strains. So there's a total of 6 strains that we're going to calculate, just like there's 6 stresses. Okay, let's do the normals first. So XX is 0.007 minus the initial, 0.01, divided by the initial. And that is negative 0.3. The YY normal strain, the final length is 0.015 minus the initial of 0.01 divided by the initial. And so that's 0.005 divided by 0.01, so that's positive 0.5. The ZZ shear strain is no change is shown, so that's just equal to 0. The final length is the same as the starting length. I wrote these wrong. These should be epsilon. That gamma is only for the shear strains. Okay, now the shear strains. Gamma xy. These are the positive faces. And so that's the angle that we're going to use. So pi over 2 minus 1.3 gives 0.271 about. We can't see the angle change between the x face and the z face, or the z face and the y face. So gamma xz is equal to gamma yz is equal to 0. So this is the complete state of strain. So we have 6 stresses with subscripts XX, YY, ZZ, XY, blah, blah, blah. We have 6 strains with the exact same subscripts. It seems pretty obvious that we would want to put the strains into a matrix of the same form, but actually we're not going to. The benefit of that matrix notation comes from the stress being this mathematical object called a tensor. And the strain, as we're defining it, is not a tensor, so there's no benefit to us to put it in a matrix. So we're just going to put it in a list of values, a 6x1 matrix, like a vector. And that's called the Voigt strain. So we're going to represent the a state of strain as a 6x1 matrix. I'm going to write that as epsilon under squiggle. It's not a vector. It doesn't have vector properties, so giving it an arrow over the top isn't really accurate, but it looks like a vector. And the format is, so, well, what do you think? Starts off good. Epsilon XX. We'll do the normals first. Epsilon YY. Epsilon ZZ. And then we'll do the shear strains. And the shear strains go in the exact opposite order of what any sensible person would do. So we'll go gamma YZ first, gamma XZ, and then gamma XY. I don't know. Maybe there's a reason for that, but I don't know what it is. It seems like a very odd choice of order, but Mr. Voigt was the first one to do it, so he got to choose. That's enough of that. Okay, so from the last example, our state of strain would be written negative 0.3, positive 0.5, 0, and then YZ, XZ, and then xy. We can also write the stress in this Voigt form when we don't need to take advantage of the fact that the stress is this thing called a tensor. So when we don't need to use the tensor properties. Those tensor properties have to do with invariance of this object under rotation. So I'll write it as the Voigt stress, and you follow the same order of elements as we did with the strain. That'll be sigma xx, sigma yy, sigma zz, sigma yz, sigma xz, sigma xy. And that's also, this is equivalent to sometimes written sigma xx, sigma yy, sigma zz, and then taus instead of sigmas. So tau yz, tau xz, bless you, tau xy. So the next thing we have to do, that's the definition of the strain. We've defined the stress. The constitutive relationship has to do with the constant factor, multiple, the constant object that we multiply to one of these to get the other one, just like the spring constant when you're talking about springs. So this is the constitutive relationship, like how the material is constituted. You know, the spring stiffness tells you how stiff or flimsy a spring is. The constitutive relationship has to do with how flimsy or stiff and a few other, a material is in resisting all these different types of deformations. Constitutive relationship. And the relationship we're going to use is that if you set up the strain in the Voigt form, that's equal to a matrix times the stress in the Voigt form. These two are each, they're like 6-element vectors. They're 6x1 matrices, so how big is this, this matrix that we're multiplying by? 6x6, yep. So this is a 6x6. This one's called the compliance matrix. Because the bigger the values are of this matrix, the easier the material is to deform. Or you can take the inverse of the compliance matrix and you get this relationship that says the Voigt stress is equal to a different 6x6 matrix times the Voigt strain. And this is a 6x6 matrix called the stiffness matrix. And this is called the stiffness matrix because the bigger the values are, the more resistant to deformation the material is. These are inverses, so it makes sense that they mean the, sort of opposite things. Okay, so a 6 by 6 matrix defining a material is bad news. That suggests that you have to do 36 careful tests of a material to figure out what the material properties are. The good news is that if your material is isotropic, you can represent these entire 36 values in terms of only 2 parameters, and those 2 parameters are really easy to measure. And I'll talk about the tensile test that you do to measure those 2 parameters. So for isotropic materials, and that's one of our assumptions. Luckily, you can represent either of these 2 matrices in terms of only 2 parameters. The first one is called Young's modulus. Or the modulus of elasticity. Or just the material stiffness. It's represented as a capital E, even though, oh, I guess it's probably the E for elasticity. I never thought of that before. And the units are pascals, or, force per area. The second one is called Poisson's ratio. And you represent it with the Greek letter nu. Is that nu? I mean, it's old, but nu, I think. Let's call it that for now. Okay, let me give you the matrix. We've come so far. I'm just going to write down this matrix. So the compliance matrix then, and I'll talk more about what these mean physically. The compliance matrix, capital C under squiggle, has this form. 1 over E, negative nu over E, negative nu over E, and then 0, 0, 0. Then the second row is negative nu over E, positive 1 over E. So this 1 over E just keeps moving through. Negative nu over E, 0, 0, 0. The third row is negative nu over E, negative nu over E, 1 over E, 0, 0, 0. Then 0, 0, 0. And in the fourth column, we have 2 times the quantity 1 plus nu over E, 0, 0. I'm pretty sure it's nu. It feels really right to say that. Then 0, and this one now in each row just moves 1 over to the right. So 2 times the quantity 1 plus nu over E, 0. And then it's in the last spot. And so what that says is if you somehow know the state of stress at a point, you don't have to know anything about what the deformation looks like. You can use this matrix, multiply it by the stress in the Voigt form to just calculate what the strain is. That's more often the case, but if you happen to know the strain and you want to calculate the stress, you take the inverse of this matrix and do the same thing.
Can you say that one more time?
Yeah, so if you the last thing about the inverse, well, just the stiffness matrix is the inverse of the compliance matrix. So if you have this plugged into your calculator, and instead you have the strain and you want to calculate the stress, just make your calculator do that inverse. It's a built-in function, then multiply it. Okay, that's all.